I am Massimiliano Pasquale. I am a visiting assistant professor here at the University of Istanbul. I started this year, and my field of research, as you already can see, is gamma ray burst. This is the first seminar of 4 seminars that will be dealing with the gamma ray burst of GRBs for short. Okay. I will try to speak slowly, but there is a lot of material to cover, so some misunderstandings can happen. So if you have a question, we'll be happy to answer them. But please keep them for the break or after the end of our seminar. Okay. No, they're all good. Okay. Gamma ray bursts were discovered by mistake, or serendipitously, if you will, in the 1960s. Those days, the USA launched the so-called Vela satellites to check whether the Soviet Union was respecting a treaty on the ban on nuclear tests of atomic bombs from space. So the USA launched these satellites that could detect X-rays and gamma rays, and with some surprises, these satellites, yes, discovered the burst of X-rays and gamma rays, but the burst did not come from Earth, but they came from space. Here is the very first light curve of a gamma ray burst, discovered on July 2nd, 1967. You can see the counts seen by this vector versus time. This is, as you know, this is a light curve. Okay. However, for a few years, nobody knew of this gamma ray burst because this was a military secret. Okay. Only in 1973, finally, data were disclosed, and the world came to know about gamma ray burst. But for several years, gamma ray bursts were just a curiosity. Nobody knew anything about them. It was only in 1991 that we started to understand something more about gamma ray burst, thanks to these satellites, the NASA Compton Gamma Ray Observatory, or CGRO for short. This satellite, this observatory, had several instruments, but the most important were BATSI, which operated between 20 kiloelectron volts and 88 megaelectron volts, and Y, which operated between 20 megaelectron volts and 30 gigaelectron volts. BATSI had the goal to discover as many gamma ray bursts possible. Indeed, at the end of his life, I discovered about 2,700 gamma ray bursts. Here you see the map on the sky of gamma ray bursts. Different colors means different numerics, but as you can see, there is no anisotropy of source positions. The gamma ray burst positions are completely random in the sky. Okay, there is no connection with the galaxy clusters of AGN or sort. So take out AGN from or neutron stars or galaxy clusters from the equation. And they are also similarly bright. This is the sky seen in gamma rays. This is our Milky Way. Okay. This is what happens when gamma ray burst goes off. Let's see whether I can make this animation start. let me use a different, the older method. Okay. Gamma burst goes off. It is like the sun. Or the rest of the sky is actually cancelled. I can show it again. Boom. Okay. So gamma bursts are extremely bright, and there is no repetition. They do not repeat. Once a gamma burst has occurred, it will never happen again. Okay. As the name suggests, the 90% of the fluence, that is the flux multiplied by time, is in photons with energy larger than 100 kilo electron volts. There are two classes of gamma ray burst. Long gamma ray burst, as you can see here, the duration can be several tenths of seconds. Usually it's between 2-3 seconds and a few hundreds of seconds. Okay. There are also short gamma ray bursts, as the name suggests. There are very short spikes of gamma rays. Long gamma ray bursts usually last more than 2 seconds. Short gamma ray bursts are less than 2 seconds, and they are also different in terms of spectrum. The prompt emission of longer gamma ray bursts here has a low hardness ratio, so it's not yet visible here. Hardness ratio on the y-axis. So they are long and low hardness ratio. It means that there are less hard photons than soft photons. Whereas in the case of short gamma ray bursts, there are more hard photons than soft photons. Hard, high energy; soft, low energy. Here is an example of these light curves. As you can see, they can be extremely different. There is a very wide range of shapes for gamma burst light curves. They can be, you can see spikes, then empty space, then spikes again, or you can see a sort of peak, then it goes down. You can also see these funny things. You have an initial spike, then silence for 30, 40 seconds, and then some major spikes. However, if you study light curves, gamma ray light curves in details, you can already infer something very interesting about the gamma ray burst. First of all, they must be compact sources. Why? Well, if for example you take the sun and you switch it off, okay, the luminosity of the sun, you see from the sun, will not go to zero immediately, because the light emitted from the border here takes 2-3 seconds more time than the light that comes from the center of the disk to reach us. There is about 700,000 kilometers. Okay, so here the light has to cover two more seconds. So when you switch off the light, when you switch off the sun, you first see a black dot here that finally covers everything. Or if you will, the variability is approximately the size of the source divided by the speed of light. In the case of gamma ray bursts, very careful analysis of the light curves showed us that they had structures of 0.001 seconds, perhaps even shorter than 0.01 seconds, but everybody at least agrees on this, 0.01 seconds. It means that the radius of the emitting source must be of the order of 3,000 kilometers, okay, as an order of magnitude. As I said, up to 1996, nobody knew where gamma bursts came from. Yes, the Compton Gamma Ray Observatory had provided us with a lot of gamma ray burst positions, but these positions had an error of about 10 degrees. 10 degrees is about 20 times the size of the sun, of the apparent size of the sun and the moon. No way we can find something in such a large region of sky. There are several probes and satellites with gamma ray detectors in the solar system. They constitute the Interplanetary Network, or IPN. There's this network can derive the position of a new gamma ray sources with a better accuracy on the order of 1 degree, but then it took those days, 20, 30 years ago, it took several days to work out, to crunch out the positions. And by the time optical telescopes observatory went to see what was there, they found nothing. Okay? So up to 1996, there was no counterpart of gamma ray burst in the X-ray, optical, or radio wavelengths. Everything we had were just gamma rays. Okay? For a few tens of seconds, and then they vanished, they disappeared. So we had no information on the distance of gamma ray burst. Were they galactic inside our own galaxy? Were they extragalactic? So we did not know anything about the energy. Because if a gamma ray burst occurs in our galaxy, well, it has a certain energy. But if it is 1,000 times or 1 million times farther away, then the energy scale is completely different. The physics is completely different. But we didn't know anything until this satellite, Vectosax. The funny name comes from the fact that it is originally it was a satellite for Astronomy X, SAX symbol, but that came from the name of one Italian pioneers of high-energy astrophysics, Professor Occhialini, nicknamed Beppo. Since he's Beppo Sax. This satellite was built by Italy and the Netherlands, and it was launched in 1996. How Vectosax basically had this kind of instrument, the so-called wide field cameras of WFC, which operated between 2 and 30 keV, so in the X-ray. But what is important, it has this kind of structure. You see, there are parts of this mask which are covered by lead. Okay, lead does not let the X-ray or gamma rays go through. Okay, while other parts are not covered, and the X-ray can actually go through. Okay, so depending on where the source of X-ray gamma rays is, there are different shades. There are different shadows cast on the bottom of this instrument. So depending on the shade, of this shadow, you can reconstruct the position of the source. This is the so-called coded mask technology, and allowed to reconstruct X-ray sources positions down to 3 arcminutes. Okay. Now, not only that, Vectosax was able to be repointed very quickly. For those days, it was peak in about 8 hours, and it could start to observe after 8 hours. It could observe the position of a newly discovered source with the so-called narrow field instruments, or NFI. Pi, which operated between 0.2 and 10 keV. So, so there is a gamma reverse. The wide field cameras pinpoint this gamma reverse down to 3 arcminutes. In about 8 hours, Earth sends command to Becosax to repoint, and the Becosax points the source with these telescopes, the narrow field instruments, which are X-ray instruments, okay? I'm sure you know it. And the result was the Becosax ball, JB 970228, was with, the wide field cameras observed and localized this longer gamma reverse within 3 seconds. Becosax was repointed, and 8 hours after the trigger, narrow field instruments started to observe the Jeremy field. Okay, and they found a new uncatalogued source. There was nothing there before. Now there was that bright X-ray source. After 3 days, the same source was observed again, and it had faded. Okay, it has become dimmer. Now with this good positioning, wide field cameras provided by WFC and narrow field instruments, optical telescopes could actually observe the position and found a new uncatalogued optical source, which was fading as well. And this was the counterpart of this new X-ray source. In the next months, people found also radio counterparts, which were fading as well. So it was in 1997 that we came to know that gamma bursts have a long-living, fading emission across the electromagnetic spectrum. This is called the afterglow. The afterglow of gamma bursts. By the way, gamma bursts take their name from the date when they happened. This one occurred in 1997, second month, February 2028, the date. Okay? Now that we knew where gamma bursts were, we managed to find that they host galaxies. Yes, gamma bursts were found to be extragalactic. They did not occur in our galaxy. They occurred outside. For example, this is GMB 990123, and this is the fading optical afterglow, and this is the host galaxy. By analyzing the spectrum of that afterglow, it was found a redshift of 1.6. Okay? It meant that, assuming isotropic emission, this gamma burst has produced something like 3.6 10 to the 54 ergs. If you want to know how much is it two solar masses converted into gamma rays. And remember, this energy is produced in a region of a few thousand kilometers and within a few hundred seconds. Okay? Hence the title of my talk are the most luminous explosions after the Big Bang itself. We also came to know that at least, I forgot to point out that afterglow were discovered in the Becosax years only for longer gamma bursts. We did not know anything for short gamma bursts for a long time. Okay. However, for long gamma bursts, we started to learn, and we found that they actually connected with supernovae. At the position of Becosax, gamma burst 98 to 42025 here, we found a supernova, a very bright supernova called SN 1998 BW. This was a very strange object. It was, first of all, it was a 1C supernova. Okay? So it's a core collapse supernova produced by a very massive progenitor, and there is no hydrogen or helium in the spectrum, which you can see here. From the spectrum, you see there are other very strange characteristics. See, usually other supernova spectrum, like those shown here, perhaps it's not very well focused, but anyway, the lines, the spectral lines, see, are usually narrow. Okay? In the case of this supernova, the spectral lines were actually very broad. This meant only one thing, that there must be very high expansion speed, as fast as 0.2 C. Okay? In addition, there were early and bright red emission, straight from supernova at early times. The absolute magnitude was minus 19.4, while what is supernova usually are 2-3 magnitudes weaker than this. So overall, it was a very strange animal, a very strange beast. We called hypernova. Supernova is not enough. We need something bigger. Hypernova. And we have found that all longer Gamma bursts at redshift less than 1 show emission from a very energetic 1C supernova. Never from a supernova 2, 1A, and 1B. All the supernovae are always redshift less than 1 is not because they are not supernovae at redshift larger than 1, but because it is very difficult for our instruments to study supernovae at redshift larger than 1. Okay? Tolga, excuse me, is not very focused. Maybe a problem with
I don't think that there is anything we can do at the moment, but one thing I can do is to dim the light. With that?
Maybe little better. Okay. See, it's not very. It's a bit blurred here.
Yeah.
Okay. And from supernova, you came to know also the host galaxies of gamma ray bursts. Here is a nice collection of host galaxies of gamma ray bursts. The faint green cross shows the position of the gamma ray burst. First thing you can notice is that there is not a single spiral galaxy, except one. This one. Other than that one, these galaxies are irregular, probably interacting, small. If they are small, also have low metallicity and have high star-forming rates. And also, from studying the positions, we came to know that longer bursts occur at the periphery of host galaxies on the bright spots of star-forming regions. So, again, longer bursts are associated with massive stars that we find only in star-forming galaxies, in star-forming regions. Okay? And these stars live short lives, usually about 1 million years, or something like that. Gamma bursts only in or close to star-forming regions. Okay? Now the picture has a bit changed. Okay? But it does not. It is still good. A good deal like that. We also came to know that gamma ray bursts are relativistic sources. How? Well, that's the radio light curve of one of the first gamma ray bursts. As you can see, in the first days, the radio flux was going up and down very widely. Okay? After about 1 month, it started to fluctuate much more slowly. Okay? We attribute this behavior to a so-called diffractive scintillation occurring in our galaxy. What is this object? We think that plasma bubbles inside our galaxy scatter radio waves and cause twinkling of radio sources. The same phenomenon that for which stars twinkle. Okay? Because stars are the angular size of the stars is very small. It's much smaller than bubbles of hot air in our atmosphere. And as a result, as the bubbles move, the light is actually bent in one direction, then toward us, then in another direction. So the stars twinkle. This is the same phenomenon on a much larger scale that occurs in our galaxy. Only when the angular size T source or the source T source is larger than the angular size of this bubble of hot plasma, it's about 3 micro arc seconds, variations end. Okay? So we knew that at about 30-40 days after the gamma reverse, the source must have a size of about 3 micro arc seconds. Okay? We knew the distance of this object because we had measured the redshift. Therefore, we could find also the radial extension of this source. By dividing by the time, we could infer the expansion field. We found that this source had relativistic expansion, relativistic speed. Okay? Something that we came to know from gamma burst afterglow, it is very important for the physics of this source, is that we came to know that the flux density is power loss both in time and in frequency. This is the flux, the X-ray flux versus time of a collection of all the gamma burst afterglows. This is a logarithmic scale, log. So power laws look like straight lines, and you can see straight lines. This is a collection of optical light curves, again log scale, and you can see again straight lines roughly. The spectrum again log, X-ray and optical. Again, we have power laws. The values of the temporal index, and it's also called the decay index, and the energy index here is typically 0.6 for alpha is typically 1.3 for the X-ray and 1 for the optical. Typically, the optical decays a bit less fast than the X-ray. As for the optical, typical energy index in the optical band is 0.6, is 1.1 in the X-ray. The X-ray spectrum is a bit steeper, usually. We also came to know that gamma bursts are not isotropic, but actually are collimated. They ejecta and their emission is actually confined, collimated into a jet of opening angle theta. How we came to know this? Because we saw changes or breaks in the decay slopes of the light curves of the afterglows. So at the very beginning, at time t1, the source is very fast, and because relativistic beaming, okay, we see the emission only coming from region which is moving actually towards us, okay? Because all the emission is beaming in the direction of motion, so only this region on the axis of the observer is actually visible. And so, I should to say, emits radiation that we can see. The emission coming from here and from here is beamed away from us. However, the ejector decelerates with time, okay? The ejector slows down, and at a certain point, gamma, the Lorentz factor of the ejector, will be equal to theta, the opening angle of the ejector. When this happens, okay, since the beaming, the beaming angle is 1 over gamma, okay, we see emission coming from all the surface, from all the emitting surface. The emission is much less relativistic beaming, okay? The ejector keep slowing down, but there is no more radiating matter beyond the angle theta. So what happens? That the light curve at this point, when gamma is proportional, I should say it's actually minus 1. Sorry, there is a mistake. It's gamma to the minus 1 here. For those that are very good at relativity. However, at this point, the emission will start to decay faster. It's what we call the jet break. And this time here, T2 is called the jet break time. Okay? These are a purely geometrical and relativistic effect. Okay? It also means that the gamma ray burst actually emit less energy than we thought earlier. Earlier, we thought that gamma ray bursts were isotropic sources, but are not isotropic sources. They are jets, they are collimated. It means that they have a much lower energy, but by how much? The true energy, okay, the energy corrected for this collimation effect is the energy, assuming isotropy, the iso, multiplied by 1 minus cos theta, where theta is the opening angle of the jet. For mod theta, it's approximately theta squared divided by 2. Okay. Now, by measuring the jet break time, the ratio, by making some inferences on the energy of the jet and the density, you can measure or you can estimate the opening angle T-jet. Okay? Typically, T-jet is the order of 0.1 radians or 6 degrees. Okay? But it's important to note that in 2001, Frey et al. Measured several E-iso, energy emitted in gamma rays assuming isotropic, and T-jet. And they found that T-jet were anti-correlated with E-iso. It meant that the higher E-iso, the smaller the opening angle. That is, this factor here was actually smaller as well. Okay? E-iso has a very wide range. You can see it in this plot here. It is the E-iso. As you can see, comes from 10 to 52 to a few 10 to 54. Okay? But when you multiply E-iso by this when you correct by the beam factor, look at what happens here. The corrected energy has a very narrow distribution, okay? And it is of the order of a few 10 to 50 Hz. So gamma ray bursts have actually have a standard energy. What changes is the beam angle of the ejector. Okay? Some gamma ray bursts are very narrow, and then they look like extremely bright. Other gamma ray bursts have a wide theta, and then they look wimpy, weak, okay? But more or less they have the same energy. By the way, if E iso and theta were not correlated, okay? If you multiply E iso by a quantity which is not correlated, okay, you should get a much wider distribution. This is what we learn at our physics courses, okay? But it is the opposite. The distribution of these two variables, combined shrinks. It's much narrower. It means we got it, okay? Now we know that the situation is not exactly like that. It's not simple. Sometimes you have gamma bursts that even after correction have very large energies or very low energies. But overall, this argument is still here with us. Gamma burst changed the research on gamma burst changed in 2004 with the launch of the SWIFT mission, which was a joint collaboration of NASA, UK Space Agency, and Italian Space Agency. SWIFT is a mission dedicated to gamma ray burst. Okay, it does a lot of other research, but it was born for gamma ray burst research, and it allows simultaneous multi-wavelength observations of gamma ray burst in gamma ray, X-ray, and UV optical, not from 8 hours after the trigger, but from 100 seconds after the trigger. And it has a very high sensitivity. It discovers about 100 gamma ray bursts per year. So far we have got about 1,200 gamma ray bursts, whereas Medusax in all its life only observed 50. 2 orders of magnitude more. Okay? It's been a revolution in gamma ray burst science. NASA sending reviews, very swift as top scientific mission, even more important than Chandra, and just after the Hubble Space Telescope. We have thousands of reference publications, including SWIFT data, which are being published. Let's see whether I can make this animation runs. No, of course not. Okay, I'm going to show it to you anyway. It is the launch of SWIFT.
15, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition, and we have liftoff of NASA's SWIFT spacecraft on a mission to study and understand gamma ray bursts throughout the universe. Everything continues to look good as the Delta vehicle climbs away from Florida's Central Coast with the SWIFT payload on board. The 3 solid rocket strap-on boosters are burning just fine. But the SWIFT spacecraft is on its way to catch in real time gamma ray bursts.
Here is a few characteristics of SWIFT. So it's a long table, so I'll try to make it simple. Basically, SWIFT has 3 instruments on board. It has the Burst Alert Telescope, or BAT, which is again a coded mass detector, like Becosax wide-field cameras, but it works between 50 and 150 dB. It has a much better sensitivity, so it is 5 times sensitivity, 5 times better than BATSI on board the Compton Gamma Ray Observatory. It has a field of view of about 1/10 of the sky and a resolution of 3 arcminutes. Sensitivity is about 1/10 to -8 erg per centimeter per second. Then there is the X-ray telescope here, or XRT, which is basically based on, it has 1/XMM CCD basically. It works between 0.3 and 10 dB, the sensitivity of the order 10 to -14 CGS units, Field of view is 23 by 23 arc minute. Resolution is 1.5 arc second. Not arc minute, but arc second. Okay? And then there is the optical telescope, which is again a copy, a spare copy of the XMM optical monitor. It works between 180 and 700 nanometers, so roughly the optical band. It can detect source as weak as 21 in 1,000 seconds. Field of view is a bit smaller than XRT. Resolution is much better, so 0.6 arc minutes, and it has seven filters. 3 UV filters, U, B, V, and Y. Now, when BAT detects a new gamma burst, SWIFT autonomously does not need inputs or commands from Earth, does it automatically. Autonomously produce in 100 seconds to start a sequence of observations with XRT and URT. It basically rotates itself and points the new gamma burst with XRT and URT telescopes in 100 seconds. By the way, it does not use rockets. Okay? It uses gyros inside it. Has been working, I should say, reaction wings. And not using rockets does not run out of gas, so it's been working for 13 years now. And when, I should say, when SWIFT detects a new gamma burst, it immediately sends text messages to ground observers with the coordinates and the first data of new gamma burst. So people, GRB observers on the ground, are told immediately when a gamma burst occurs. In 100 seconds, they have the coordinate and they can start observing the new gamma burst. Let's slide and make a break. These are summary of the main results for the SWIFT year. We now observe X-ray and optical light curves of gamma burst from 100 seconds to 10 million seconds after the trigger, and we found some canonical behavior. I'll explain to you what it means canonical. We have found the first X-ray afterglows, optical afterglows, in the redshift of short gamma bursts. So finally we know short gamma bursts where they come from. There have been several incredible discoveries of SWIFT. For example, we had a gamma burst 080319, which reached an apparent magnitude of 5 from redshift 1, with a few tenths of seconds. It means an absolute magnitude about -38, -39. Okay? It's the naked eye gamma burst. If you had to observe the right direction, you would see a new source, which was at redshift 1 from here. Gamma bursts were detected at the redshift of 9.4, okay? Only 400 million years from the Big Bang. Gamma bursts are farther away than any AGN, and only few galaxies have been discovered farther than this gamma burst reaching 9.4. We have discovered several gamma bursts similar to 98 to 425A, with the association with the supernova I showed you earlier. We found that we discovered a few cases of shock breakout events from supernova. We have seen supernova exploding. People were observing a galaxy, and all of a sudden they saw a burst of X-ray. But it was not a gamma burst. It was a star which has just gone supernova. Very cool. We also found a new class of gamma bursts, the so-called ultra-long gamma bursts, which last more than 10,000 seconds. We also found a few relativistic tidal disruption events, or TDEs. They happen at the center of some galaxies when stars go very close to the center of supermassive black hole. tidal forces break the star, and some part of the material falls into the black holes and powers a bright but transient emission. In some cases, the matter moves at relativistic speed, and these are relativistic cases, which are rare, but very bright. Okay, I think we can stop for say 10 minutes, and then we start again. Okay. Statistics of Swift gamma afterglows. Thanks to Swift, 98% of gamma bursts have an X-ray afterglow. Okay. 60% of gamma bursts have an optical afterglow. However, this is 90% if they are followed up by ground observatories systematically with optical and near-infrared, near-air instruments. Okay, and about 33% of gamma bursts in the Swift era have a radio afterglow. Before Swift, only 30% of gamma bursts had an optical afterglow, but thanks to Swift, we have doubled or even multiplied by 3 the number of gamma bursts that have an optical afterglow. Okay? One of the most important discoveries of Swift is the so-called canonical X-ray light. Canonical means that it is a canon, it is a standard, it is something that happens all the time. Okay? As I said, we have a very large number of X-ray afterglows. Okay? So we can study some general trends of gamma bursts. We found that typically, as you can see from this plot here, you can see the flux in X-ray versus time. Typically, X-ray afterglows, okay, start with a fast decay. This is the prompt emission, the gamma ray emission. Then Swift starts with about 100 seconds after the trigger, and see this fast decay. Okay. Then there is a phase between 1,000 seconds and 10,000 seconds, more or less, in which the flux decays less fast. Okay, we call it a plateau. It's a French word which means plane. Okay, the decay slope here is 0.5. Okay, so the flux is going like times to the minus 0.5. Here the fast decay was going as time to the minus 3. Okay. Then at about 10 to the 4 seconds, we have the so-called normal decay. Remember when I said about the Becker-Sachs gamma burst with a decay slope alpha of 1.2, 1.3 in the X-ray? This is this phase. Okay? Thanks to Swift, we know that this phase starts about 10 to the 4 seconds after trigger. And finally, in a few cases, we also see a fourth phase of steep decay with a decay slope of about -2 that starts about 10 to the 4, 10 to the 5 seconds after the trigger. This is very similar to what we see in the optical after the jet break. Remember that the jet break, the optical flux starts to decay much faster. This is the same condition in the X-ray, at least we think. In addition, we saw the so-called X-ray flares. This is an important argument. In a few gamma ray bursts, okay, superimposed on this light curve, we see sharp rise of the X-ray flux, like this one. For example, you see the X-ray flux was going down, was as a light curve, then all of a sudden, boom, it goes up, and then it goes down again. As I said, these are the so-called X-ray flares. They are important because they are not produced by the same mechanism which is producing this X-ray afterglow. Okay? We know this because the spectrum, the X-ray spectrum here, is very different from the spectrum at other epochs. And in addition, the mechanism that produces this power law decay cannot produce this very fast variation of flux that we see in X-ray flares. We think that these X-ray flares are the X-ray version of those spikes in gamma ray band that we saw during the prompt emission. Okay, remember that the prompt emission are those spikes. Those are in gamma rays. These are instead in X-rays. But the prompt emission in gamma rays can last usually a few tens, maybe a few hundreds of seconds. Flares in X-ray can happen up to 10 to the 5 seconds, almost 1 day after the trigger. It means that the mechanism that produces the prompt emission, somehow it is still active up to 1 day after the trigger. That's why it is a very important discovery, the X-ray flares. Okay? And then, other than the X-ray, we also have the canonical UV optical light curve. Here you see a collection of optical light curves discovered by the Swift UV optical telescope. And you see here, in several cases, we see early peaks. You see here, at about 1,000 seconds, we see peaks in the optical light curves. We do not see peaks in the X-ray. Okay? We want light curves have early peaks. X-ray tip light curves do not. Often, and after that, often yes, we have a plateau, a phase of slow decline of the flux in the UV optical as well, but it is different from the X-ray because sometimes the plateau in the X-ray, in the optical, carries on, continues, while in the X-ray it is actually interrupted. And we see the standard normal decay. It doesn't happen all the time, but sometimes it happens, and it is a problem for the models that try to explain the X-ray and optical together. Here is a collection of early peaks, and as for flares, yes, we also see flares in the optical. They are the counterparts of the flares we see in the X-ray, but they are not so prominent as those in the X-ray. The X-ray can be very bright and very evident. In the optical, no, they're not so strong as they are in the X-ray. Here is a global view, or a broad view of optical light curves of gamma bursts. They are put together. Colors means have a meaning, but not going to explain to you. This is basically the R-band magnitude of a collection of a large collection of gamma burst afterglows seen in the Swift year. As you can see, a few gamma bursts have this initial very bright peak, okay, followed by a very fast decay, or sometimes we just see a fast decay. Then we see a phase of slow decline on the flux, okay. But this is rare. usually gamma ray bursts do not show these very bright peaks. Okay? Typically, gamma ray bursts, just optical afterglows, have a peak at the beginning, followed by a slow decay. Okay? So we have few cases which have a very bright initial peak, followed by a steep decay, and then a shallow decay. Or we have a peak, a less bright peak, followed by a slow decay. This is important because it means we have different mechanisms that are producing this emission. Well, sometimes we don't see the peak, the initial peak, but there is no reason to think it's not there. Probably it's just us that do not start observations fast enough. Sometimes we just see the initial slow decay or the initial fast decay. Okay? And after a few days, we see the jet breaks. The optical flux starts to decay very fast. And then we have also this template behavior for the radio afterglows of gamma ray bursts. As you can see, there is a very large span of radio luminosities, but overall the behavior is more or less decaying. Typically, we have a dip 2 days after the trigger. Then, at about 10 days after the trigger, we have this sort of peak here. And then, after a few tens of days, say a few months, okay, we see this fast decay, which is again probably the jet break seen in radio. It is important to note that observations in radio can last years. Usually afterglows are not observable anymore after a few days, maybe 1 month if it is a very bright object. But in radio, you can follow up afterglows for many, even for years. This is important because at late times there are phenomena we want to study. Okay? We can study them only in radio. Typically, radio at this peak, the radio afterglows has a flux density of the order 500 microjansky. They are faint sources. Okay? It takes very large radio telescope like the EULA to observe this kind of objects. Finally, as I said earlier, we found the afterglows of short gamma ray bursts. In 2005, Swift directed the first X-ray afterglow of a short gamma ray burst of 5 or 9B, thanks to the fast repointing. It was here is the night scale X-ray flux versus time. It was very faint. It was going down fast. It was going down fast. It was gone. It was vanished after 1,000 seconds. Okay. Here is the gamma ray light curve. You see the peak of this short gamma ray burst. But even if this was a weak, a dim source, thanks to the X-ray afterglow detected by Swift, we could find the position. Okay, the error period of the XRT instruments was this one, 9 seconds, and within these 9 seconds, we saw this very bright galaxy, which was very bright with a K-band magnitude of 14, and it was elliptical. Okay, it is very different from the host galaxies or longer gamma ray bursts. Remember, those are small, blue, and have a lot of star formation. This galaxy is actually large, red, and no star formation. In addition, there was no supernova associated with this short gamma burst. All of this is telling you that the progenitors, the thing that produce short gamma bursts must be very different from what produces longer gamma bursts. By the way, since this object, since this short gamma burst, we detected about 100 short gamma bursts, we have never seen a supernova. Okay? Even though these objects were observed with very big telescopes, very big, but never seen even the faintest supernova. Never. These days, 95% of short gamma bursts have an X-ray afterglow. Okay, 35% have an optical afterglow. 7.5% have a radio afterglow. You can immediately see that these numbers are lower than those for long gamma bursts. The reason is short gamma bursts are weak sources, are weaker than long gamma bursts. In general, Swift does not see a lot of short gamma bursts. In 13 years, only 100. There have been more than 1,000 long gamma bursts. Okay? Here is okay, on average, X-ray, optical, and radio afterglows of short gamma bursts are weaker than those of longer gamma bursts. Here is an example. These are the gray lines are the optical afterglows of longer gamma bursts. The red points are the optical afterglows of short gamma bursts. As you can see, they are systematically fainter than the first one. Okay? By about 3-4 magnitudes. Okay? We find gamma bursts only at lowish redshift, typically between 0.09 and 1.7. Okay? While long gamma bursts are found between 0.14 redshift and 9.4. Again, this is also because they are weak sources. On average, the gamma ray energy emitted by short gamma bursts, assuming isotropy, is typically 2×10⁵ Hz. Okay? Whereas long gamma bursts, on average, emit more or less 5×10⁵ Hz. There is more than one order of magnitude. Okay? In a few cases, short gamma bursts show jet breaks. And if they show jet breaks, you can infer the opening angle of the jet. And we found this typically 0.3 radians. Okay? While in long gamma bursts, it is typically 0.1. So not only gamma bursts, short gamma bursts are weak, but they're also less collimated. The opening angle is much wider. And by correcting for collimation, the energy is emitted is of the order of 8×10⁴ Hz. Okay? It is one order of magnitude less than the energy emitted by longer gamma bursts after correcting for collimation. In 2008, there was a new mission, Fermi, which has allowed us to discover a lot of new things about gamma bursts. It was originally called GLAST, but then was named after Enrico Fermi. It carries only two instruments: the gamma ray burst monitor, or GBM, which works between 8 kV and 100 MeV. It has a very wide field of view, half of the sky. And it also carries the Large Area Telescope, or LAT, which works at very high energies between 30 mega electron volts and 300 giga electron volts. It has a bit smaller field of view of the order 2.4 steradians, but it's still quite large. When a gamma burst is observed by LAT, it's also observed by GBM. It means that we can study the gamma burst emission from 8 kilo electron volts to 300 giga electron volts. Okay? So it's about 8 decades, 8 orders of magnitude in energy. And in the giga electron volt band, Fermi is the most sensitive facility ever built. And thanks to Fermi, now we know that afterglows are also in the GB band. On the right, you can see plots of the GV emission detected from some gamma ray bursts. This GV emission lasts typically a few hundred seconds after the trigger, well after the end of the prompt emission, which is visible in the mega electron volt band. Okay? Photons with energy up to 10 giga electron volts are detected, and more important than ever, the light curve is still a power law. Okay? Power laws are the hallmark, are the mark of gamma burst afterglow. Okay? And this log plot, you see that the GV emission is a power law. Okay? Look, this is what happens this is what Fermi sees when there is a bright gamma burst with GV emission. Here you see the emission at low energy. Okay. Here is the emission at very high energy seen by LAT. Okay. And here is the number of GV photons. Okay. You see that at low energy, in this gamma burst, at low energy up to 1 mega electron volt, the emission was over after 20 seconds, okay? And ended 20 seconds after the trigger. But these red dots are LAT photons detected by the LAT at GeV energies, and you see, they carry on. Now we have to talk about the prompt emission. So far we have talked about afterglows, but now we have to talk about the prompt emission. The spectrum of the prompt emission is strange. People have tried to understand its behavior, but there's still a lot of debate about the cause of this emission. Here is a plot. There are plots of flux, and the flux multiplied by energy versus energy of gamma burst prompt emission. We find in 20 years ago, Mr. David Band found that this expression can fit the prompt emission of gamma burst. Indeed, this is the fit of the prompt emission following this theoretical model. Now, it looks complicated. It is roughly, it is the two power laws smoothly connected. Okay? Here's a power law. Here the power law. Here is the smooth connection between these two power laws. Okay? We also have this index, this low energy index, usually called alpha, here, which is the slope of this part. We also have beta, which is the high energy index. Okay? And Typically, alpha is -1, beta is minus 2. And the connection between these two power laws is at the energy is 0, which is called the break energy. And what is important is that this peak energy, this break energy 0 is connected to the so-called peak energy, E peak, or EP for short, okay, at which most of the energy is radiated. If you plot, this is the plot of nu F nu energy multiplied by flux density, okay, versus energy. This gives you how much energy is radiated at that energy, and you see that this is the peak, EP, and this can be calculated as E0 multiplied by 2 plus alpha. Okay? Usually, since alpha is -1, more or less, E peak and E0 are very close to each other. And typically, it is 300 kilo electron volts. Okay? But it changes a lot between gamma reverse. By the way, this fitting here is purely empirical. Okay? There is no theoretical explanation behind it. Simply, Mr. Band tried several models until he found that this one works. But it has no theoretical explanation. At least we know any theoretical explanation. Now, if you know the peak energy in the observer's rest frame, okay, you can easily compute the peak energy in the rest frame of the burst is multiplied by 1 plus z, but z is not the redshift, okay? If a gamma burst at redshift 1 has the peak energy at 300 kilo electron volts, it means that in the cosmological rest frame of the gamma burst, the photons at the peak energy had the energy of 600 kilo electron volts. Okay? So the cosmological peak energy EPI is easy to get. Once you know the shape of the spectrum and you know the distance, okay, and you know the energy, you can calculate how much energy the gamma burst produced. Okay? Again, assuming isotropy. You need to know the spectrum, the redshift, and the R, which is the luminosity distance in cosmology. But it is a function of redshift Z. Okay? As you can see from these two plots that show the distribution of the cosmological peak energy and the cosmological energy emitted in gamma rays, gamma iso, these two variables have a very large span, okay? From a few kilo electron volts to thousands of kilo electron volts at peak, and the iso can be as low as 10 to the 50 or even 10 to 48, up to 7 10 to 54. However, Mr. Amati found that there is a very strong correlation between the peak energy in the cosmological frame and the gamma ray energy, the total energy emitted by the gamma reverse. You see, this correlation is very strong. The chance is that the probability that it's there by chance is 10 to the minus 18. It's 0. The correlation is real. Amati found that the peak energy is roughly proportional to the energy emitted in gamma rays, assuming isotropy, at the power of k, where k is 0.57. Okay? And it applies to long gamma reverse, does not apply to short gamma reverse. These are long gamma reverse, these are short. See, they don't follow the Amati relation, the Amati relation. Okay? The manipulation was formed 15 years ago with deposit data, and it has been confirmed by Swift and Fermi. Even with very energetic bursts that have very high peak energies, very high energy releases, or bursts that have very low peak and very small energy emitted, this relation still works, still applies, is still true. Okay? It covers, as you can see, it covers something like 5 orders of magnitude. I should say that a few people do not believe that this is real. A few people think that it is an effect of our instruments, okay? That do not observe gamma bursts here and here. But most researchers in this field believe that it is actually real. Okay? So Fermi has allowed us to study gamma bursts because it has a very good sensitivity. GBM instruments detect about more than 200 gamma bursts a year. Half of these instruments, of these gamma bursts, are in the LAT field of view, but the LAT observes only 10 of them. Okay? For some reason, a lot of gamma bursts that GBM detects do not emit GV photons. We don't know why. I mean, probably only very bright gamma bursts can produce an emission visible by both GBM and LAT. But if you have a weak gamma burst, then probably GBM can still see it, but LAT cannot. But there may be also other reasons. It's possible that the spectrum has a cutoff of very high energy. Also, I should say that most people think that a few gamma bursts have a prompt emission which is very bright in the mega electron-volt band, but it falls down at GV band. We don't know yet why. Well, as I said, it's very important that GBM and LAT cover this very wide energy range. These days we have huge catalogs of GBM and LAT bursts. So what are the most important discoveries that Fermi has given us? We found that the GV emission is delayed. It comes late with respect to the mega electron-volt emission. The bound model fits the prompt emission for most gamma bursts over 8 orders of magnitude. But this is true only for 70% of gamma bursts. For 30%, that bound model, that smooth broken power law, okay, doesn't work. You need other components. You need, for example, a power law. You need a cutoff, or you need a thermal component. Why it's like that? Nobody knows for sure. Okay? And also very important, the spectrum itself can evolve. It does change, sometimes dramatically. I'll show you in a second. Here again is this plot shows the light curves at different energy bands: low energy, middle energy, very high energy, and finally the LAT band. Okay? This shows, unfortunately, it's not clear, it's a bit blurred, but the red, this is the spectrum. Okay? This shows the spectrum. The red is the spectrum at the very beginning. Here, it has this shape. Then we have the green, which is roughly here. See, it has changed shape. Then we have the blue. We have this new component, a very high energy. See, it was not here before. It showed up at about 15 seconds. And then at later than 20 seconds, we have this purple here. You see there is a power law here now. Power law which was not there before.
So the red one's high energy cutoff? Which one is?
The energy cutoff is visible in the blue spectrum between, if I read correctly, is 10, between 10 and 20 and 20 seconds. It's about here. You see the cutoff at high energy. There is this component, but at about 500 megaelectron volts, because it goes down. Okay? And later this cutoff disappears because it is here the spectrum is going like that. What is interesting here at late epochs that this component here shows up at very high energy, but it also shows up here. See, it's not going down as there was no other component. There is something here which is pushing up. So this is a summary of what we have said today. Gamma ray bursts are very bright and not repeating sources of gamma rays that occur randomly in the sky. They are characterized by fast variability, lasts from typically 0.1 seconds to 10,000 seconds, roughly. Okay? They are followed, gamma ray bursts are followed by GV, X-ray, optical, and radioactive loss that can last roughly weeks. Okay? After emission is a power law both in temporal and spectral domains. This is the flux density. It is a power law in both time and energy, or frequency. Okay? Change in temporal decay indicate gamma ray bursts are collimated, not isotropic sources. If you assume that there are isotropic sources, then the energy can go up to 10 to the 24, 10 to the 25x. Okay? And they are cosmological. They can occur up to redshift almost 10. From very low redshift, 0.01, to redshift of 10. Okay? The fifth mission has enabled us to discover about 100 gamma ray bursts per year. So provided a very large statistics of gamma ray bursts, and that enabled us to study the aspect law starting 100 seconds from the trigger with instruments on Swift itself, the X-ray telescope and the optical telescope, and from the ground. Long gamma ray bursts, those that last more than 2 seconds, okay, are associated with very energetic supernovae, and they occur in star-forming galaxies. Short gamma ray bursts, less than 2 seconds, are not associated with supernovae and occur in all kinds of galaxies, including elliptical, red, and non-star-forming galaxies. Okay? The Fermi mission, another mission, just contributed a lot to our knowledge of gamma ray bursts, can observe the prompt emission from 8 kiloelectron volt to 300 gigaelectron volt. Usually the prompt emission spectrum can be fitted with a simple model, the band model, but sometimes multiple components are necessary, and the spectrum evolve with time. The prompt peak energy, and the total energy released E gamma iso, sorry, I forgot the E gamma here, are correlated. Okay? This is a sum. I think that's it for today. If you have any questions, I'm happy to answer. Yes?
You didn't mention about magnetars. You didn't mention about magnetars in short gamma ray burst case.
I do it in the next semester. Okay. I could not cover everything today. We have 4 segments. So yes, magnetars are a very important topic for short gamma ray bursts, even for long gamma ray bursts actually, and because we think that they can produce enough energy to power gamma ray bursts. But we see more in the next semester. Okay?
Sorry, I am curious about the effective area of both Fermi and Swift, does the effective area has decreased during this period?
Thank you very much. No, it's actually, well, Swift has lost about 20% of its gamma ray detectors.
Yeah.
But because sensitivity, it is old vision, okay? But its sensitivity changed with the square root of the number of detectors. So even if it has lost 20% of detectors, its sensitivity is down by 10% only. So it's not really a problem. I'm not sure about Fermi. I think Fermi is more or less okay.
Yes.
You had a question? Yes?
You said at the beginning of the slides that there is no repetitions about the gamma ray. So, do you mean that there are any gamma ray bursts at the same place, or do you mean
Never.
that?
Never.
I mean, you mean also they are non-periodics?
No,
it's okay.
no, I meant to say that gamma ray burst never repeats. We have never observed two gamma ray bursts coming from the same place. Never. There is a class of objects that look like gamma ray bursts, but they are not gamma ray bursts. The so-called soft gamma ray repeater, SGR, those repeat. But indeed, they are not gamma ray bursts. They're typically galactic sources, or they occur in the large Magellan clouds. Okay, but they are different. They look similar because it's gamma ray emission, a burst of gamma rays, and then but these are different objects. By the way, the fact that gamma ray bursts occur only once and then never again is already telling you that something catastrophic is happening. Something that can happen only one time, only once. The explosion of a star, the collisions of stars, something like that. Okay, any other questions? Okay.
One more question. You said we can divide the gamma ray bursts like two main groups. One is bright peaks and fast decays, and the other one is not bright peaks and slow decays.
Yes.
So, can we understand this like there's actually one gamma ray burst, but maybe the surface area of what the beam is coming from is bigger or lesser? What can I say?
If I understand your question, I would say that the answer is no, because we have made models for this gamma ray burst emission, and we don't think that the difference there is the area of the emitting surface. Okay? Bear in mind that, for example, if gamma ray bursts have an initial Lorentz factor of say 100, okay, then you can always see only 100 of radian of the emitting surface. Even if the gamma ray burst has a very large emitting surface or very small, if gamma is 100, then you see always 100 by 100 radian. Okay? And typically we find that indeed the Lorentz factors of gamma ray burst initially are about a few hundreds. They do not change a lot. Okay? We think that for those events which have bright peak, we think that in a few cases, there are rare events, okay? There is one additional different mechanism that is producing all that bright emission. We'll talk to it in the next segment. Okay? But they are spectacular. The gamma ray burst that occurred 08 or 319b occurred at redshift 1, meaning about 12 billion light years from us. Okay? And it became visible by night time. Think how bright it was.
Yeah.
Precious one. Any other question? Okay. Not see you next week. I forgot to give you my email address, but it's like my name, m.Pasquale@istanbul.eu.pr. So if you don't want any further questions, please look.